Sections 3.8 to and including 3.10 on groundwater. This figure shows groundwater in a homogeneous aquifer captured between two impermeable layers, one at the bottom and one at the top. The water level in both canals lies above the bottom of the upper impermeable layer, causing the aquifer to be confined. The canals are incised to the top of the lower impermeable layer. For this, the expression fully penetrating canals is used. Because the water level in the left canal is higher than in the right canal, groundwater flows from left to right through the aquifer. The water in the canals is artificially kept at the levels indicated in this figure, this level and that level. Because of this, groundwater flow is steady, or in other words, stationary. The top of the lower impermeable layer serves as the reference level. At x is 0 meters, the hydraulic head in the aquifer, H0, equals the water level in the left canal. At x is L, the hydraulic head in the aquifer, HL, equals the water level in the right canal. In each point of the vertical in x is 0, the hydraulic head, or potential, has the same value H0. If we were to install a piezometer with its screen here, then this would be the elevation head and this would be the pressure head. If we were to install a piezometer with its screen here, this would be the elevation head and this would be the pressure head. Elevation head plus pressure head is hydraulic head, so everywhere along this vertical we have the same hydraulic head, and thus the vertical in x is 0 is an equipotential. The same reasoning goes for the vertical in x is L. Each point of the vertical has the same hydraulic head HL, and the vertical in x is L is also an equipotential, albeit with a lower hydraulic head value than at x is 0. Because the steady flow is from left to right and is confined between two impermeable layers, flow must be horizontal and at a right angle to both equipotentials in x is 0 and x is L. In other words, all verticals between x is 0 and x is L are equipotentials, with their hydraulic heads diminishing from left to right. Darcy's law for this flow case can be written as the volume flux Q equals minus K times A times HL minus H0 divided by L. HL minus H0 is the difference in hydraulic head. L is the distance over which this difference in hydraulic head occurs. So HL minus H0 divided by L is the hydraulic gradient. A is the area perpendicular to your water flow, and K is the hydraulic conductivity. This can also be written in the following shape: for an increment delta x along a streamline and a corresponding difference in hydraulic head delta H, Q, the volume flux, equals minus K times A times the hydraulic gradient, written as delta H delta X. If we take delta X infinitely small, we can write dH dx instead of delta H delta X for the hydraulic gradient. As A is the saturated area perpendicular to the groundwater flow inside this confined aquifer, this area A equals the vertical depth of the aquifer times the width W, which is the horizontal direction perpendicular to this cross-section, so going into the screen. And we can write that Q equals minus K times D times W times the hydraulic gradient dH dx. We can divide the volume flux Q by this horizontal direction perpendicular to this cross-section W and then obtain Q with a prime equals minus KD times dH dx. Q with a prime is the volume flux or discharge per unit width of the aquifer. Per unit width actually means that we dispose of the width of the aquifer so that we only deal with the horizontal X and vertical Z dimensions of the cross-section. The volume flux per unit width, Q with a prime, has units of square meters per day, much the same units as the ones that you use when you paint your garden fence. In hydrological practice, groundwater flow problems are usually reduced to 2 dimensions in cross-section or plan view, simply for ease of calculation. Because the aquifer is homogeneous, the hydraulic conductivity K has the same value for every horizontal position X. The saturated thickness or depth D is also constant for every horizontal position X. Because the water in both canals is artificially kept at the levels indicated in this figure, and the volume of water entering the aquifer per unit of time to the left must equal the volume of water leaving the aquifer per unit of time to the right, there is, so to speak, no creation or destruction of water flow per unit of time within the aquifer. The hydraulic gradient must be the same for every horizontal position X. Thus, the hydraulic head linearly decreases with horizontal direction X. Mathematically, this linear relation between H and X can be written as follows. H equals C1x plus C2. Please note that in this figure, H0 has been taken as 10 meters, L as 100 meters, and HL as 8 meters. This picture also nicely shows how you can measure the hydraulic head in the confined aquifer by placing a piezometer tube with its screen within the confined aquifer. We could also have derived this linear equation for the hydraulic head H with horizontal position X, H equals C1x plus C2, as shown in the Mathematics Toolbox M1 at the end of my book. We will combine Darcy's law with the continuity equation. And this is standard procedure in hydrology. We will also be doing this, combining these equations for other flow cases. So here we have Darcy's law, here we have the continuity equation. When we combine these two for this flow case, this is the equation we get. Minus Kd times your hydraulic gradient is constant. Of course, K and D are constants, so we simply get dH dx is constant. We write that constant as C1. When we integrate this equation, this is what we get. What follows now is also standard procedure. We want to find out the values for C1 and C2. And you can find these values by inserting the boundary conditions. You always start off with inserting your left boundary condition, followed by inserting your right boundary condition. Let's start off with the left boundary condition. When x equals 0, then H equals H0. Insert this into the equation and we get H0 equals C1 times 0 plus C2. So H0 equals C2. C2 equals H0. Let's now insert the right boundary condition. When x equals L, then H equals HL. From this it follows that HL equals C1 times L plus C2. And of course we already know that C2 equals H0. So HL equals C1L plus H0. So now we have found C1 as equaling HL minus H0 divided by L. Now insert these values for C1 and C2 in the original equation H equals C1x plus C2. Inserting the values found for C1 and C2 in that equation gives this final equation H equals HL minus H0 divided by L. Multiply this by x and then plus H0. HL minus H0 divided by L is the slope of your hydraulic head distribution, your potentiometric surface or your piezometric surface, and HL minus H0 divided by L is of course your hydraulic gradient. Also, this equation, derived from combining Darcy's law, the flow equation, with the continuity equation for steady groundwater flow, is called a Laplacian, after the French astronomer and mathematician Pierre-Simon Marquis de Laplace. When H0 is taken as 10 meters, L as 100 meters, and HL as 8 meters, this equation could also have been written as stated here. Groundwater flow can experimentally be shown to be subject to refraction. This figure shows two streamlines when a steady groundwater flow passes from an upper layer with a hydraulic conductivity K1 into a lower layer with a hydraulic conductivity K2. The volume of water leaving the upper layer per unit of time must be equal to the volume of water entering the lower layer within that same unit of time. The water balance equation or continuity equation can then be drawn up as follows. The volume flux in layer 1, Q1, equals the volume flux in layer 2, Q2. Note that Q carries a prime. This means that the dimension, the y direction, perpendicular to the drawing plane of this figure, is left out of this equation. The volume flux Q with a prime, therefore, is expressed in units of square meter per day. As is customary in hydrology, we will combine this continuity equation with the flow equation, Darcy's law. Darcy's law for layer 1 states that the volume flux in layer 1 in square meter per day, Q1 with the prime, equals minus K1 times A times delta H1 divided by L1, with K1 being the saturated hydraulic conductivity of layer 1 in meter per day, A being the width of the area perpendicular to the groundwater flow in layer 1 in meter, and delta H1 being the difference in hydraulic head in meter over distance L1, also in meter. Similarly, for the lower layer 2, we can write that Q2 with a prime equals minus K2 times B times delta H2 divided by L2. Because the line with width A is perpendicular to the steady groundwater flow, the hydraulic head is the same for every position along this line, or in other words, the line denoted with A is an equipotential. The same goes for the line with width B, but the hydraulic head here, lying downstream, is lower by an increment delta H. This increment, or difference in hydraulic head delta H, is the same for both the right and the left streamline, albeit that for the right streamline, delta H is established over a shorter distance L1, and for the left streamline over a longer distance L2. Thus, the hydraulic gradients differ, but delta H equals delta H1 equals delta H2. Inserting the flow equations into your continuity equation for delta H equals delta H1 equals delta H2 gives us this relation. Please note that the tangent of alpha equals L1 divided by A. Angle alpha, here we have 90 degrees minus alpha, so also here we have the angle alpha. And that the tangent of beta equals L2 divided by B. Here we have beta, here we have 90 degrees minus beta, so here again we have the angle beta. If we insert that into this equation, so the tangent of alpha is L1 divided by A and the tangent of beta is L2 divided by B, we get the following. The ratio K1 over K2 equals tangent alpha divided by tangent beta. Now, as an example, give the hydraulic conductivity K1 the value of a clay layer in the order of 10 to the power minus 5 meter per day. And give the hydraulic conductivity K2 the value of a sandy layer in the order of 10 meter per day. The ratio K1 over K2 then equals 10 to the power minus 6. Play around with the formula, insert a value of alpha and find out what beta is, or work the other way around. Insert a value for beta and find out what alpha is. No matter what you do, with the ratio K1 over K2 being 10 to the power minus 6, you will always find for alpha a very small angle and for beta an angle that's nearly 90 degrees. And this has a very important implication. In a setting of horizontally layered sediments, for instance a semi-permeable clay layer overlying a sandy layer, groundwater flow in the sandy layer is almost horizontal and in the clay layer almost vertical. We can make very good use of this in our groundwater flow models, as we will see. This picture shows us steady groundwater flow through 4 horizontal homogeneous layers in a confined aquifer between 2 fully penetrating canals with different water levels. Groundwater flow is steady or stationary, and the boundary conditions are fixed. This means that the hydraulic gradient is the same for each layer. Continuity, the water balance, teaches us that the volume flux, or discharge, through the confined aquifer equals the sum of the volume fluxes of each layer. The volume fluxes are expressed per unit width. The direction perpendicular to this figure thus in square meters per day. And again, we can insert Darcy's law, both for the aquifer as a whole and the separate layers, into this continuity equation. We obtain this equation. Dividing by the constant value of minus I gives the following end result. Thus, in a confined aquifer consisting of horizontal layers, the Kd value for the aquifer as a whole equals the sum of the Kd values of each layer. This Kd value, in English we call this the transmissivity, in Dutch de Kd-waarde, is a measure of how easily an aquifer transmits water and has the same unit as the volume flux Q with the prime, that is, square meter per day. As we know the values of K1, 2, 3, and 4, D1, 2, 3, and 4, and their sum D, we may derive the hydraulic conductivity for the aquifer as a whole, K, from this equation. This K, without a subscript, is called the substitute hydraulic conductivity. It is the hydraulic conductivity in meter per day that we can assign to the aquifer when dealing with the aquifer as one entity instead of 4 separate layers. This figure shows steady upward groundwater flow, or seepage, through an aquitard consisting of 4 horizontal homogeneous semi-permeable layers, layers with a low hydraulic conductivity. To quickly distinguish from horizontal flow cases, the vertical hydraulic conductivity of the semi-permeable layers is presented in lowercase, and the saturated depth or thickness of these layers in lowercase d. As the water flows steadily upward in the direction of the lower hydraulic head, as can be seen by the water levels in the piezometer tubes with their screens at different depths, the volume of water per unit of time that is transported remains the same, as it's neither created or destroyed on its way. Thus, continuity, the water balance, teaches us that the vertical volume flux, or discharge, is the same for every homogeneous semi-permeable layer, as stated here. D is the sum of D1, 2, 3, and 4, and the total difference in hydraulic head over all homogeneous semi-permeable layers, delta H, equals the sum of the differences in hydraulic head over each homogeneous semi-permeable layer. For a constant area A perpendicular to the water flow, we may divide the volume fluxes in the continuity equation by this area A, as shown here. Dividing the volume flux by the area delivers the volume flux density. Thus, the volume flux densities, small q in meters per day, are equal to each other. As the total difference in hydraulic head over all homogeneous semi-permeable layers, delta H, equals the sum of the differences in hydraulic head over each homogeneous semi-permeable layer, dividing this by the constant value of Q, which equals Q1, which is equal to Q2, etc., delivers this equation. Darcy's law for vertical groundwater flow, as stated here, etc., in combination with this, gives us this. The depth of the total aquitard divided by a substitute hydraulic conductivity equals the depth of layer 1 divided by the hydraulic conductivity of layer 1 plus the depth of layer 2 divided by the hydraulic conductivity of layer 2, etc., which can be simplified to C equals C1 plus C2, etc. C, defined as D divided by K, is the hydraulic resistance or vertical flow resistance in days. The total hydraulic resistance C of a number of horizontal homogeneous semi-permeable layers equals the sum of the hydraulic resistances of each layer. This relation is useful when calculating the vertical volume flux density through horizontally layered semi-permeable layers. As we know the values for K1, 2, 3, and 4, D1, 2, 3, and 4, and their sum D, we may derive the hydraulic conductivity for the equitard as a whole, K, from this equation. This K without a subscript is the substitute hydraulic conductivity, as mentioned before, for vertical groundwater flow. It is the hydraulic conductivity in meter per day that we can assign to this equitard when dealing with the equitard as one entity instead of 4 separate layers. When calculating Q, the volume flux density through horizontally layered semi-permeable layers, good use can be made of the substitute hydraulic conductivity K, as the vertical volume flux density Q is equal to the substitute hydraulic conductivity K in meter per day times the hydraulic gradient. The above derivations provided insight in applying continuity and Darcy's law. What do we need to know? For steady horizontal groundwater flow, the volume fluxes per unit width, Q with a prime of horizontal homogeneous layers, may be added up. As a consequence, as the hydraulic gradient is the same for all layers, the Kd values or transmissivities T may be added up. For steady vertical groundwater flow through horizontal homogeneous semi-permeable layers, the volume flux densities Q of each layer are equal. As a consequence, the hydraulic resistances C of these layers may be added up. Please note that the hydraulic resistance C in days is essentially different from the travel time of water particles, also in days. For the latter, of course, we need to know the effective porosity in order to first determine the effective velocity of the groundwater. As a tip, exercise 3.10.6 from my book can be solved by applying the exact same principle of continuity and its consequences that were just derived for steady vertical groundwater flow through a series of homogeneous semi-permeable layers, but now for steady horizontal groundwater flow through a series of homogeneous aquifers. In effect, it is the same problem, but rotated 90 degrees. This figure nicely shows both horizontal and vertical groundwater flow. It is a vertical cross-section through an unconfined sand aquifer and a confined sand aquifer separated by a confining layer, a clay equitard. From the piezometer tubes in the confined sand aquifer, we can establish the potentiometric surface for that aquifer, and evident from that is that groundwater flow is from left to right. The water level in this piezometer tube rises above the ground surface, so this is an artesian well. Also in the upper sand aquifer, groundwater flow is from left to right, as is evident from the water levels in these piezometer tubes. In the clay aquitard, we have upward seepage, as can be concluded from the water levels in these piezometer tubes. I wish you success with the exercises of sections 3.8 to and including 3.10.